All right, so thanks everybody for being here. This morning we'll start with our the first lecture from Lingrui, who will talk to us about quantitative global theory and its applications. If you have questions during the talk, I'll try to relay them to Lingrui. The floor is yours now.
Thanks for the introduction. So first, I'd like to thank the organizers for the invitation. It's a great opportunity to share the ideas. Okay, my talk is about quantitative global theory and its applications. So in general, I will have two talks. Today is the first talk, and this talk is about a joint work with Professor Svetlana Jelinskaya from Georgia Tech, Professors Jiangong Yu and Qi Zhou from Chen Institute, Nankai University. So, and today's talk is based on one paper that can be found on archive here. So the archive number is here. Okay, now let's start. So we start from the almost massive orbiter. And this orbiter, so Lana and Vincent already talked a lot about this orbiter, so I will just give a brief review here. So the almost massive orbiter here is a three parameters family orbiter. So it contains two parts. The first part is just a discrete Laplacian, and the second part is diagonal matrix. And on the diagonal part, it is just some very simple real analytic function 2 lambda cosine 2 pi theta, taking the value over the irrational rotations. So this is called the almost massive orbiter. So as you can see, in this orbiter, we have three parameters. So this alpha, so it just means the rotation here is irrational, and we call this alpha frequency. And we also have a starting point on the unit circle. This is the phase. We call it the phase. And here we have another parameter called the coupling. So we have three parameters. And this orbiter is very typical in the study of the spectral theory of quasiperiodic Schrodinger orbiters. So there are two famous problems related to this orbiter. So one is about, since we have a self-adjoint orbiter, so we can consider the Lebesgue decomposition of the spectral measure of this orbiter. So related to this aspect, there is a famous conjecture called the Andre-Aubry phase transition conjecture. And this conjecture was completely solved by Jelinskaya in 1999. And what is interesting is that for this kind of orbiter, there is a phase transition phenomenon. So as when the parameter lambda changes, so the spectral property of this orbiter will change. For example, when lambda is smaller than 1, then this orbiter will have a purely absolutely continuous spectrum. Actually, this is a measure sense in the measure sense for almost every alpha and theta. And actually, we also have the arithmetic descriptions of this four measure set of alpha and theta. So, okay. Actually, this one in later this result was proved by Avila that it holds for any irrational alpha and any theta. Actually, it also holds for rational alpha. So for any alpha and theta, it holds. It has a purely absolutely continuous spectrum. But when lambda is equal to 1, then the spectral property will change. This orbiter will have only purely singular continuous spectrum. So the spectrum changes from absolute continuous 1 to singular continuous 1. But then when the parameter is larger, when it is larger than 1, then it will have Anderson localization. Anderson localization just means it has fewer point spectrum. So, and all eigenfunctions decay exponentially. So all these results was proved for almost every alpha and theta in this paper. Okay, this is one famous conjecture related to the Lebesgue decomposition of the spectrum measure. Another problem is about the topological structure of the spectrum. So for this orbiter, we have the spectrum, and for its spectrum, it's conjectured that this orbiter, the spectral set of this orbiter is nowhere dense perfect set. So it just means it is a contour set. So this is called the Taine-Martini problem, and this problem, this result is conjectured to be true for any irrational alpha and any lambda non-zero lambda. So when lambda is 0, then this is just this orbiter is just the free Laplacian. So the spectrum is the interval. So for this problem was proved by Avila and Jasinska in 2009. So these are two important conjectures about the spectral properties of the almost Martial orbiter. So for many years, many people spend a lot of time to study these two problems, and finally these two problems was solved for the almost Martial orbiter, but only for the almost Martial orbiter. So from the point of, from our point, it's natural to ask the same question for general real analytic functions. So just for almost Martial orbiter, it is very special because the potential is 2 lambda cosine 2 pi theta. This is a very simple real analytic function, right? 2 cosine theta is the basis of in the Fourier expansion of the real analytic function. But the above two results only hold for the almost Martial orbiter. But so it's natural to ask whether the above questions hold for general real analytic, if the potential is a general real analytic function, one periodic real analytic function. So this asks to consider a more general orbiter. So this is called the one frequency analytic one frequency shielding orbiter. Here we have a general real analytic one periodic real analytic function as the potential. So for this orbiter, one will have similarly we will have two questions. One is about the Andre-Aubry phase transition conjecture. But as you can see here, for this general case, we even do not have any parameters. For almost Martial orbiter, we have a parameter lambda here. But in the general case, we do not have any parameter. So in this case, how to formulate this Andre-Aubry conjecture is the question, right? So one question is, so how to formulate this Andre-Aubry conjecture, and how to prove, if one can formulate, then how to prove. Another question is about the Taine-Martini problem. So this problem is very clear that if we replace 2 lambda cosine 2 pi theta by a general one periodic real analytic function, then if in this case, whether in this case the spectrum is still a contour set. So, but we should avoid some trivial case, which f theta should be a non-constant real analytic function. So the Taine-Martini problem will be this one. So the spectrum is a contour set if f theta is a non-constant real analytic function. So whether these two questions hold for general one frequency orbiters, this is our question. So this is also the starting point of today's talk. Actually, in many years, people do not know how to deal with these two kind of questions. One very important recent breakthrough is Avila's global theory. So Avila's global theory actually enables us not involve any parameter in this potential. So one can formulate the Andre-Aubry phase transition conjecture in a purely dynamic system way. So in this case, we need to consider the dynamical objects corresponding to the shielding orbiter. It is the so-called Schrödinger cycle. So the eigenequation of the Schrödinger of the Schrödinger orbiter can induce this Schrödinger quacycle. It is a map from T times R2 to itself. So here T means one-dimensional torus. This map maps the first coordinate theta to theta plus alpha, and maps the second coordinate, this vector v, to a theta times v. This a theta is the 2x2 matrix of this form. So this special form is also why we call it the Schrödinger quacycle. In general, if this is just a 2x2 matrix, then we call it a quacycle. But if this a theta has a very special form, we call it the Schrödinger form, then we call it the Schrödinger quacycle. Since we assume this function is analytic, so one can check this map, this matrix maps the torus to SL2R. SL2R just means this matrix has determinant 1. So here C omega just means this is an analytic map. So we have an analytic 2x2 matrix with determinant 1. This is called the Schrödinger quacycle. And since this map is analytic, then by the theory of complex analysis, one usually know this. One can extend this map to a neighborhood of the torus. So one can also define this matrix in the neighborhood of the torus. So the crucial discovery of Avila is he finds that there is a dynamical object to describe the Andrei-Aubry phase transition conjecture. So it is called the Lemma exponent of the complexified quacycle. Actually, before Avila, or many years ago, people already know there's a close relation between the dynamic systems and the spectral theory, and to use Schrödinger quacycle to study the spectral theory of Schrödinger orbiters. So many people know this idea, and they also know for this quacycle one can define the Lemma exponent, but only in the real case. So only define the Lemma exponent for the Schrödinger quacycle. Avila's new idea is to define the Lemma exponent for this complexified quacycle. So this is called this complexified Lemma exponent. And actually, this if we consider this complexified quacycle, then we can easily check it belongs to SL2C. So by Kingman's sub-additive ergodic theorem, this limit one can still consider this limit, and this limit still exists, and so this complexified Lemma exponent, Lyapunov exponent is well defined. So this is Avila's new idea. Moreover, so before Avila, people just know this some property of this Epsilon E. It is proved by Bourgain and Jesniska in 2002 that this L Epsilon E, if you view it as a function of both E and Epsilon, so it is continuous in both variables. But I will find more. He found that if one fix this energy E, just consider this L epsilon E as a function of epsilon. So here for 2 pi epsilon, just for some normalization. So you view L epsilon E as a function of this epsilon, then I found this picture is extremely simple. So it is an even function and a convex function. Moreover, the most interesting thing is this L epsilon E is a piecewise affine function, and all the slopes are integers. So we have a piecewise affine function. Here is K1, K2, K3, just the slope. So it seems this is a very beautiful picture, and later we will talk more about this picture. Actually, this picture is the foundation of Avila's global theory. Okay, now let's continue. As I said before, the almost Messier orbiter is a protypical model. So once one develop one theory for shielding orbiters, so people always first try it for the almost massive orbiter to see if this theory is if this theory is very complete, right? And also did this. He found that if one calculates this Epsilon E for the almost massive orbiter, then we will only have 4 cases of pictures. So the first case is actually one can decompose this R, the real the set of real values of R into the spectral set and the relevant set. And I'm gonna calculate all this energy E. If we found if E is in the relevant set, if it is not in the spectrum, then the picture looks like this one. And the most interesting thing is for all E, the picture is the same. So this is the picture for the E's that are in the relevant set, and for E in the spectrum, the situation is more complicated. We find that in general there are three different pictures. One is for lambda smaller than 1. When lambda is smaller than 1, we find that the initial lambda exponent is 0. Then one have a flat piece here. So this is the for in lambda smaller than 1 case. And for lambda larger than 1, then the picture lambda equal to 1, then the picture is different. The original lambda exponent is still 1, but one does not have a flat piece, right? Okay, this is the difference. And when lambda is larger than 1, one will have another different picture. The initial lambda exponent is larger than 0, and there is no flat piece. So in general, for any E in the spectrum, we will have 3 different kinds of pictures of this Epsilon E for the almost massive orbiter. So if you still remember the Andre-Aubry phase transition conjecture I introduced at the beginning, then you will find exactly they are of the same philosophy. If one sees the picture of Epsilon E, there is also a transition. So when lambda is from lambda smaller than 1 to lambda larger than 1, there is a transition of this picture. So this motivate want to relate the different spectral type to the picture of this Epsilon E. So this is exactly a very big contribution of Abraham's global theory. He found this relation. And let's recall that for the Andre-Aubry phase transition sets, in this picture case, we have AC spectrum. And in this picture case, we have singular continuous spectrum. And the last case, we have pure point spectrum. And so to distinguish these different pictures, I will introduce the one important quantity called the acceleration. Because as you can see in these above pictures, the different thing is if for the original lambda, if there is a flat piece, right? The flat piece just means the slope is 0. So the acceleration is motivated by these pictures, and it is defined in this way. Maybe you can also see this in the blackboard. So it is the L epsilon E minus L0 E over 2 pi epsilon. Then one take the limit of epsilon goes to 0 plus. So this just means the slope of the first piece in the above picture. So just means the slope of this first piece here. And for almost massive orbital, one will find that the acceleration is always for about 4 pictures. The acceleration is either 1 or either 0. So here is 0, and the other case are just 1. So later I will also talk about this value. This acceleration actually plays a central role in investigating the spectral theory for quasiperiodic orbitals. But in general, I will prove that this value is always a non-negative integer for general real and negative functions. So for general real and negative functions, the value can be 2, 3, 4, or any integers. That's the difference between almost Massive orbital and any other orbitals. Later we will talk about this. Actually, this value will also this value of this acceleration will affect the spectral properties. Okay, this is the acceleration, and based on this acceleration and the Lemma exponent, then I can decompose the spectrum into 3 different regions. So just like the almost Massive orbital. So as I said, so it seems that there is a relation between the picture of this Epsilon E and to the different spectrum, right? So then to describe the exact correspondence, I will decompose the spectrum into 3 types. The first one is called the subcritical. It just means here Lemma exponent and the acceleration are both 0. Just means the picture looks like this. So we want the original Lemma exponent is 0, and one also have a flat piece. And also the critical one is like the critical almost Massive orbital. Also, these names are from almost Massive orbital because for the above picture of almost Massive orbital, this is subcritical almost Massive orbital. This is critical almost Massive orbital. This is supercritical almost Massive orbital. So in general, one can also decompose the spectrum according to this picture of Epsilon E. So the supercritical one is just means the Lemma exponent is larger than 0, and the acceleration is larger than 0. So it seems as you can see, these pictures looks like the subcritical, critical, and the supercritical almost Massive orbital, but there is a difference. The difference is here. For the slope of the first piece, that does not need to be 1. For almost Massive orbital, these slopes are both 1, or 1. But for in general case, it can be any integers. That is also why for more general orbitals, the spectral theory is much more complicated because this value is no longer 1. Okay, then I will conjecture give such a conjecture that the subcritical one just behaves like small like potentials. Small like potentials just means it has pure AC spectrum. This is proved by Edison in 1992. So I will conjecture that the subcritical region will only support the pure AC spectrum. So like the subcritical almost Massive orbital. So there is a correspondence between these regions and different spectrums. And the supercritical one behaves like big like potentials. So in this case, it is expected that they will have pure point spectrum. So this intuition will give us the very beautiful formulation of Andrew-Aubrey phase transition for general one-frequency Schrodinger orbitals. Okay, one can formulate the Andrew-Aubrey phase transition conjecture for general one-frequency Schrodinger orbitals in this way. So the subcritical region can only support the absolutely continuous spectrum. Actually, this can be proved by a conjecture called the almost reducibility conjecture. Later, I think in tomorrow's lecture, I will talk about this conjecture. So anyway, once this conjecture is true, then one can prove the subcritical region corresponds to the purely absolute continuous spectrum. So this is the first one. And the second one is the critical region, like the critical almost Massive orbital, will only support the singular continuous spectrum. This is totally open now. And for the supercritical region, it is expected that in this region, one will have pure point spectrum, even one has Anderson localization. And this was only proved in some measure sense. So for fixed theta, for measures, for almost every alpha, one has Anderson localization. But to prove the Anderson localization in a purely arithmetic way, this is still open. So it is open in the arithmetic sense. So give an arithmetic description of the frequency to prove Anderson localization in this region is still still a big problem. Okay, and also with this is the first motivation of our today's talk. So why we want to develop the quantitative global theory? This is one motivation, because the global theory gives us a very big picture here, but just use the global theory, one does not know how to prove this correspondence. So our quantitative global theory is towards this direction. So we aim to use the quantitative global theory to establish such correspondence, but this is still far away for the complete picture. And also for the time-matinee problem, one can, with the help of the global theory, one can also has some decomposition. One can decompose the time-matinee problem into 3 different regions. So if you want to prove time-matinee problem, then you only need to prove that the first one is the subcritical region cannot contain an interval. So this is widely open. And the second one is the critical region cannot contain an interval. So this is already proved by renormalization theory by Avila Feiner and Kurikorin. So this is finished. And the last one is the supercritical region cannot contain an interval. So in this case, the results are also in the measure sense. So in the arithmetic case, it is still open. So if one can give this arithmetic description of the frequency and prove that in this case the spectrum cannot contain an interval, this is still open. Okay, so this is another motivation to use quantitative global theory. Can we use this observation?
还是想做老师呢，还是搞那个设置啊、动脉啊等等，这个是有用南宁大、工艺大学。
Sorry about that. It should be all right now.
Okay. Oh, okay. Can I continue now? Okay, I will continue. Okay, so let's continue. This is anyway. In this case, I just means global theory provides some hope to solve the time-matinee problem or Andrew-Orbit conjecture for general one-frequency shooting orbitals, but it is still widely open. Just to use the global theory, so one needs more tools. Okay. Next, let's talk about the almost reducibility conjecture. So as I said before, this conjecture is related to 1/3 of the Andrew-Orbit phase transition conjecture. So the subcritical can only spot purely absolute continuous spectrum. So actually, in this case, I will reduce this correspondence to one famous conjecture called the almost reducibility conjecture. And if one proves this conjecture, then this correspondence can be established. So for this case, one only needs to prove this conjecture. This conjecture will imply that the subcritical region can only spot the purely absolute continuous spectrum. Okay, in my tomorrow's talk, I will talk more about this conjecture. Next one is okay. Now we can introduce our quantitative global theory. So as I introduced at the beginning, in our global theory, the foundation is the picture of this Epsilon E. So this Epsilon E is a piecewise affine function, and all slopes are integer. So when I first saw this picture, I asked myself several questions. Actually, I think these questions are very natural. So the first one is why these slopes are integers? So in general, this is strange, right? The slopes are all integers. So in some sense, we can call them index. Another one is, so what are the turning points? I will only prove that there are some turning points. And the third one is, if I know the turning points and know the slopes, is it helpful to the study of the spectral theory of shooting orbiters? So are the exact value of these turning points and the slopes important? Actually, these questions we will answer these questions in our quantitative global theory, and in later tomorrow. Okay, maybe in my tomorrow's talk, I will talk about actually this exact value of the slope, and these turning points are very important to study the spectral theory. So to make it clear whether what are the turning points, what are the slopes, actually we later find that this is crucial to the study of the spectral theory. Okay, how to describe this picture? Then this is the main question. And this is our recent work, our work about quantitative global theory, and how to find these turning points and these slopes. Actually, after I established build his global theory, in a long time, people don't know how to find these guys. So we spent a long time to find actually there's a relation between this picture and the orbit duality. So this is one very important point, to use orbit duality to see this picture. And actually orbit duality was introduced for one frequency shooting orbiter a long time ago, but for a long time people don't know. People don't know. Before our global theory, people do not know how to establish, how to combine orbit duality and global theory together. So once one combines this orbit duality and global theory together, one will find many hidden mysteries. So let me briefly introduce this orbit duality. It is, you can just think of this orbit duality as some Fourier transformation. So you have some transformation to transform this original one frequency shorting orbiter to another orbiter. So this orbiter, we call it the long range orbiter. But the bad thing is you transform a finite range orbiter. So here we have a second order difference orbiter to a infinite dimensional infinite difference orbiter. So one do not have any dynamics now. So a good way is first consider the trigonometric polynomials. So once one consider the truncation of this native function, so is here this f is a native function. Then if you consider the truncation of this native function, you only consider the sum of first 2D terms. This is the trigonometric polynomial. And in this case, if you consider orbit duality, you will get a finite difference orbiter. And the good thing is, in this case, you will have dynamics as the second order case. Recall that in second order case, we introduced the Schrödinger cocycle for the second order orbiter. And similarly, for this 2D orbiter, 2D difference orbiter, one can also introduce a cocycle called the dual symplectic cocycle. But in this case, the cocycle is more complicated because we will have a higher dimensional cocycle. It is a 2D by 2. This A hat is a 2D by 2D matrix. So it maps T times C times C to 2D to itself. So we will have a more complicated cocycle. But in some sense, this cycle is good in some sense because the potential is now is simple. The potential is cosine. This looks like the almost massive orbital, but only with more complicated the difference part. Okay, for this symplectic cycle by the dynamic system tools, one can still define the Lemma exponents. But like the eigenvalues, just think about the eigenvalues. If we consider an SL2R matrix, we will have two eigenvalues, lambda, lambda 2 inverse. And if we consider a 2D order, the 2D by 2D symplectic matrix, one will have 2D eigenvalues. So similarly, in this case, one can also define more. One needs to define more Lemma exponents. So actually, we will have 2D Lemma exponents, but due to this complex symplectic structure, one will only have D non-negative Lemma exponents. So they come into positive and negative pairs. So one will have more Lemma exponents in this case for the dual model. So as I said before, actually we need to consider an infinite difference operator. So in this case, we do not have any dynamics. So one cannot define the Lemma exponent. So our strategy is first consider its truncation, then define the Lemma exponent. Then an important theorem is that we proved that for this Lemma exponent defined by the truncation function, they are Cauchy sequence, not for all Lemma exponents, but for the first m Lemma exponents. So there are several minimal Lemma exponents. So first, for example, for the first 100 Lemma exponent, they will converge when d goes to infinity. So for any real analytic function f, actually one can define the Lemma exponent of an infinite difference operator in an approximation way. So you approximate this function f by fd, then define the Lemma exponent for fd. Then we prove this Lemma exponent for fd converges for the first m Lemma exponents. That converges to some point, and we call this limit point as the Lemma exponent of the infinite difference operator. Actually, why we call them the limited Lemma exponents, because they play the same role as the finite dimensional case, the Lemma exponent of the finite dimensional case. So anyway, for infinite difference case, one can still define the Lemma exponent in an approximate way. And assume we call this Lemma, this guys the dual Lemma exponents for the long range operator. And now we can group this Lemma exponent in this way. So assume we have k distinct Lemma exponent, and the multiplicity of this Lemma exponent for the first one, it is the multiplicity is n1. For the second one, the multiplicity is n2 minus n1. Okay. If we group the Lemma exponent in this way, then one can find the hidden mystery in this in the picture of this Epsilon E. Here, we find that we can give a complete description of the picture of the Lemma exponent by the dual Lemma exponent. Actually, we found that the turning points are exactly those dual Lemma exponents, the distinct dual Lemma exponents. And here, the slope just means the multiplicity of different Lemma exponents. For example, when we cross this turning point, this n1, then the slope will increase n1. This is just the multiplicity of this n1. And when we cross this n2, then the slope will increase n2 minus n1. So this is exactly the multiplicity of n2. So we have such an exact picture. So this picture, the most important thing I think for this picture is we find some way to we find the turning points. To find these turning points are very, very important for us. Otherwise, we don't know which direction to prove. And actually, this picture, once one have a very concrete description of this picture, it will enable us to give many spectral applications. These values are also very important in spectral applications. For example, one direct application is to give a new classification of equivalent classification of different regions as Avila. So Avila, as I said before, the decomposition of the spectrum is very important because there is a correspondence between the subcritical, critical, and the supercritical and the spectral type. Right now, we can use our new observation, our new result to prove a new classification theorem. We can prove that the subcritical is equivalent to this case. So the original lemma exponent is 0, and the dual lemma exponent are all positive. Actually, later tomorrow I will talk about, I will say about this. This is the basis of ARC, of our new proof of ARC. So this observation gives us some before our result. People don't know why people only know to use almost localization to prove almost reducibility, to prove some non-perturbative version with small potentials. But in the global sense, how to use almost localization to prove almost reducibility, it is not known. But this result tells us the dual of subcritical is supercritical in some sense. So one can use the localization method to prove reducibility result. So this is a very crucial basis of the almost reducibility conjecture. And the second one is the critical one. The critical one means the original lemma exponent equals to 0, and the minimal lemma exponent of the dual operator also equal to 0. So this also explains why critical is so rare, because one will have 2 0 lemma exponents. So I will prove that in the major sense there are no critical. So in this case, one can also have some intuition about his result. So it is rare because one have 2 0 lemma exponents. And the remaining one is about the supercritical. The supercritical means the original one is larger than 0, but the dual operator will have 0 lemma exponent. So roughly speaking, we have such a very symmetric picture. The subcritical of the Schrödinger operator and the supercritical of the dual operator are equivalent. And in another side, that the supercritical of the Schrödinger operator is equivalent to the subcritical of the dual operator. So this will establish the bridge between the Schrödinger operator and the dual operator. So that means one can involve different tools to deal with these two operators together. Okay, so this is one important corollary of our quantitative global theory. Now let's give some more quantitative calculations of some quantities in Avela's global theory. So the first one is about the quantitative calculation of this acceleration. So as I said before, acceleration plays a central role in the study of the spectral theory. So it is meaningful to give more calculations of acceleration. So actually, by our quantitative global theory, we can give such a calculation of the acceleration by its dual lemma exponent. We proved that this acceleration equals to the multiplicity of the 0 lemma exponent of the dual operator. So here we just consider only non-negative lemma exponents. So this is a calculation of this acceleration. More importantly, we find that there is a connection between the lemma exponent to some dynamical system object. We proved that actually, if if the potential is a trigonometric polynomial, so in the trigonometric polynomial case, one can define a dual cocycle. This is a symplectic cocycle. We can prove that this cocycle is partially hyperbolic. So this is a very, very crucial thing for spectral applications. This here, partial hyperbolicity just means, so we have a decomposition, continuous decomposition of C2T. So this is the most contracted one. This is the most expanded one. And EC just means the centered action. We proved that if the acceleration is larger than 0, then the dimension of the centered action equals to 2 times the acceleration. So you can see this partial hyperbolicity is just some dynamic system object. And we connect the centered action of this, the dimension of the centered action to this value of the acceleration. It also explains why when acceleration is very, very large, is larger, then the problem will be more complicated, because you will see when the acceleration is larger, then the dimension of the centered action will be larger. So this is also explains why it is more complicated. This also explains why in Ivan's global theory, he only considers the first piece. As we know, for the picture of this Epsilon E, it is a piecewise affine function. So we have many pieces. But I will only consider the first piece, since the acceleration is defined to be the slope of the first piece. So for the classification of the spectrum, one only need to consider the first piece. Why we only need to consider the first piece? This also explains, because the other pieces will correspond to some hyperbolic part in the dynamic system. So this is some intuition in dynamic systems. Why for our global theory, the first piece is the most important part. Okay, this is the calculation of the acceleration. Now I'd like to give another calculation about this subcritical radius. So this subcritical radius is defined in this way. It is the supremum of this Epsilon E. So where Epsilon E equals to 0. So just consider this picture. So this is the subcritical. And the subcritical radius just means the turning point, the first turning point here. And we proved that it is a very easy consequence of our quantitative global theory that this subcritical radius equals to the minimal Lamb exponent of the dual orbital. So this gives some motivations for us to prove the almost reducibility conjecture, because usually the subcritical radius is in the almost reducibility side. It is related to some analytical radius in almost reducibility. While this error hat, the minimal Lamb exponent, is the localization length. So it is related to the decay rate of the eigenfunctions in the localization side. So this also motivated us to use almost localization for almost reducibility. So this is another motivation of our proof of almost reducibility conjecture. Actually, this exact value of this subcritical radius is very, very important to many quantitative spectral applications. For example, we use this subcritical radius of almost massive orbital to give some sharp estimate of the decay rate of eigenfunctions or the decay rate of the spectral gaps for almost massive orbital. So anyway, this exact value of the subcritical radius is important for quantitative spectral applications. Okay, this is the calculation of the subcritical radius. And for more applications, so actually more important applications will be we will talk about tomorrow. And today, let's sketch the proof of the multiplicative Jensen's formula. So this is, so as you can see today, I only talked about our first paper, this paper on the archive. And let's sketch the proof of this paper. So this paper actually are motivated by one important formula given by Pugh and Harrow, where they proved that the lemma exponent equals of the original Schrödinger orbiter. So there's a relationship between the lemma exponent of the original Schrödinger orbiter and the non-negative lemma exponent of the dual orbiter. So they proved that the lemma exponent of the original Schrödinger orbiter equals to the sum of non-negative lemma exponent of the dual orbiter plus some normalization. This is some normalization value. So, and their proof in a purely spectral way, because they use the invariance of the integral identity of states under orbital duality. So they use the Soros formula and the invariance of the integral identity of states. So for a long time, people don't think of to develop a non-self-adjoint version of this formula. So actually, people do not think of in this way. And our crucial thing is to build such a formula for in the case when V is not a real analytic, when we consider the complexified orbiter. So since we need to consider this Epsilon E, since this is Avla's global theory, foundation of Avla's global theory, it consider this complexified potential. And when we consider this complexified potential, although it is a non-self-adjoint orbiter, but one still have orbital duality. So the first thing is that we calculated the orbital duality of this orbiter. It is the dual orbiter is in some sense in very simple way. In this sense, up to a transformation of, so this should be 2 pi n epsilon. So if we consider a hyperbolic transformation, so this is a diagonal matrix, and we will find if we consider the dual orbiter of the complexified orbiter, Schrödinger orbiter, there is a clear relationship between it and the original orbiter. So they are similar to each other up to a such a diagonal matrix. This matrix is, the important thing is that this matrix is not unitary because this epsilon is larger than 0. So this is not a unitary transformation. It will change the spectral properties. And for this dual orbiter of dual orbiter, we can still define a cocycle, but now it is also not complex symplectic, but one can still define the lemma exponents, right? Because one can define the lemma exponent for any cocycles. And one found by this simple relationship, there is a very simple relation between the lemma exponent of this cocycle. This is the cocycle corresponding to the dual of the complexified orbiter, and this is the cocycle corresponding to the original one. So there is also a very simple relationship between the lemma exponents of this cocycle and the original cocycle. So assume for the original dual of cocycle, we have the lemma exponent gamma 1 to gamma d. So we have d non-negative lemma exponent. Then for this orbiter, it will have the lemma exponent up to some addition of 2 pi epsilon. So the lemma exponent of this a hat epsilon is also very simple. Then we proved that there is a similar formula for Pugh and Harrow's formula. We can prove this is still the lemma exponent of the Schrödinger orbiter. We can prove, but now the lemma exponent of the dual orbiter will change because the lemma exponent as a lemma exponent plus some original lemma exponent plus some 2 pi epsilon. So for example, this is smaller than 0, but if 1 plus some 2 pi epsilon, it will become larger than 0, right? So one will see that when epsilon is larger and larger, then there will be more and more non-negative lemma exponents. But thankfully, we can prove that in this case, there is still the sum of the non-negative lemma exponent still equals to this epsilon E. So this is crucial in some sense to prove the picture of this Epsilon E. But unfortunately, that Pugh's proof fails for this formula. So although it is in some sense very important for us to find this formula, but when we find such a formula, we spend a lot of time to find this formula. But when we find the formula, we find to prove this formula is non-trivial, because we cannot use Pugh's proof because he uses the spectral method. Now the operator is non-self-adjoint. One can define any spectral objects. One cannot define spectral measure or integrate Daniel test. So something like that. One cannot use spectral method. Instead, we will use the purely dynamic system method. And this method turns out not useful for just only this problem. We find this method also works for some other problems. So I will talk about the application of this method, more applications of this method tomorrow. So now let's get our proof of this non-self-adjoint of Pugh and Harrow's formula. So the first one is to build. So this formula is about formula of Lemma exponents. So our first step is to build the Lemma exponent, the relationship between the Lemma exponent and the average the Green's function. So if you are familiar with the self-adjoint case, it is the non-self-adjoint case of the famous Johnson-Motor theorem. But now one should use only dynamic system method to prove this formula. Originally, Johnson and Motor uses some spectral method, but it does not work. So we need to use dynamic system method to prove this Johnson-Motor formula to relate this the derivative of the Lemma exponent to the average Green's function. Okay, the second step is to use orbital duality to build a equality between the average the Green's function of the original Schrödinger orbital and the average the Green's function of the dual orbital. Okay, so this is our original Schrödinger orbital, and this is the dual finite range orbital. They are both non-self-adjoint, but for Green's function, it is well defined. So one can instead use spectral measure or integrated Daniel test. One can use the invariance of Green's function. So this is one important step. The next step is to calculate. Now we transfer this Lemma exponent to the dual Green's function. So the next step is to calculate the dual Green's function. And how to calculate the dual Green's function? The Green's function of the dual orbital. So since this dual orbital now is non-self-adjoint, so for its Green's function, one need to use purely dynamic system method to calculate this dual Green's function. And one crucial thing in this step is to prove that, as I said before, this dual system is partially hyperbolic. So this is important because if once this guy is partially hyperbolic, then one can use this partial hyperbolicity to create solutions of this eigenequation in a purely dynamic system way. So one can use this partial hyperbolicity to create some solutions. So actually we can create 2D solutions. We will find some of them belongs to L2Z plus, and some of them belongs to L2Z minus. And if you are familiar with the Green's function of the 2×2 case, so there is a formula for the Green's function of the 2×2 case. So once one have a L2Z plus solution and a L2Z minus solution, then one can use a purely dynamic system way to calculate the Green's function. So in the higher dimensional case, for finite difference orbital, So one can still have such a formula. So we proved that for this finite difference operator, if we have, for example, we have m L to the plus solutions and 2D minus m L to the minus solutions, then one can give a formula of this Green's function. Okay, by using these solutions. So this is a purely dynamic system way, and also this is I showed Fearman's homework. This is for 2x2 case. This is a homework. Actually, this is also one can also consider this as a homework. It's something like the constant variation in the in our for ordinary equation. Okay. Anyway, one can have in the finite difference case, once one have L to the plus solution and L to the minus solution, one can also calculate the Green's function. Sorry, perhaps I need another 3 more minutes to finish this step. Okay, thank you.
Maybe 2 more minutes, Lingrui.
Okay, thank you. Okay, when we have the formula for this Green's function, then we can calculate the dual Green's function by the solutions. And the next step is to relate the dual Lemma exponent to the dual Green's function. This is called the Johnson-Moser theorem for finite range operator. This is actually this also has more. This Johnson-Moser theorem will for finite range operator will also have more applications in our future work. And then, as you can see, for these steps, we linked the dual Green's function to the original, the Green's function of the original operator. And here we have a relation between dual Lemma exponent and the dual Green's function. And we also have a relationship between the Lemma exponent of the original operator and the original Green's function. So this will lead to this formula. There is the relationship between the Lemma exponent of the original operator and some partial sum of the dual Lemma exponent. Then we can recover the relationship between the Lemma exponents. So here it is just for the derivatives. Then one can use this equality for derivatives to recover the relationship between the different Lemma exponents. So this is the whole proof. I think I should stop here. Thank you so much.
Thanks a lot. Thanks a lot, Lingrui. We may have time for some. Do we have questions from the audience for Lingrui? Yes, Sylvius. Yeah, or ask it, and if he doesn't hear, I will relay.
So my question is about the statement that subcriticality implies the positivity of the Lyapunov exponent of the dual Lyapunov exponent. If I understood correctly, the L1 for this the limit as the dimension goes to infinity of the last non-negative Lyapunov exponent of the 2D by 2D cycle. So how do you get the smallest moment? So I would think that you need a uniform in the dimension lower bound.
Lingrui, do you hear the question?
Yeah, so sorry, I cannot hear clearly about it.
Yeah.
It seems it's far away.
Sylvius, I'll ask you to come. It's a more complicated question than I can relate, so I'll ask you to come and ask it.
The question is how you get this uniform in the dimension.
Just if you just stand by here.
Okay. Yeah. So the question was, how do you get that? I think it was L1 hat positive from the subcriticality, or how do you get that the L1 at scale D is uniformly bounded away from 0 uniformly in the dimension?
Yeah, this is a use approximation, and by our global theory, these turning points are stable in some sense in the approximation case. But But this turning point, sorry, wait a minute. Yeah, for here. Actually, by Avala's global theory, the original picture of Epsilon E is of this sense, and one can use the global theory to prove all these turning points are stable for our approximation. So once one have some the turning points of trigonometric polynomial case, one can use approximation, and one can use combine Avala's global theory. One can prove that this these approximations are stable. But this only holds for in this strip because we need this epsilon is smaller than h. So for those gamma I d, if they are strictly smaller than h, in the limited case, they will be stable. So they will be Cauchy sequence, not for all their exponents. So I mean, for the trigonometric polynomial case, if the d is larger than larger, we will have more and more Lemma exponents. But the stable one is only some finite. Finite is only finite because we need this condition. They should be smaller than h. For those Lemma exponents, they're only finite many. And combine Avala's global theory, actually one can prove those finite many are stable. So they will be the same if d is very, very large.
Do we have other questions for? Yes, David, if you can come.
Hi, it's David. So if the Schrödinger operator is subcritical, sorry, if the Schrödinger operator is supercritical, the dual operator is subcritical, yes?
Yes, we already proved this. It is subcritical.
Yeah, I just wanted to set up the question. So what can you then prove? I mean, can you prove sort of some almost reducibility of the portion? I mean, sort of that corresponds to.
So yeah, that's a very interesting question. So one can formulate this conjecture. So for high dimensional cocycles, but it is in some sense it is of the same difficulty as prove the almost localization for orbitals with acceleration larger than 1. So we can only prove in this case. I mean, this dual orbital is subcritical. So we have a center direction. If the center direction is 2 by 2. So then we can prove this subcritical conjecture now. But if it is 4 by 4, if we have 4 zero Lemma exponents, then this is now it is out of reach. Yeah.
We have maybe one more question for Lingrui. All right, let's thank Lingrui again.
Thank you so much.